Welcome back, everybody. We are talking about angular momentum and also moment of inertia. So, moment of inertia, remember, is just like inertia. It wants to resist change in motion. Well, if you have rotational inertia, which is a moment of inertia, it resists turning around in a circle. So the farther you can get the mass distributed away from the pivot point, the sluggier that it will be, the more resistant to change it will be. So the slower you can get it to spin in a circle, or once it's spinning, the slower it takes to stop it. All right, so all of these have different formulas, and I would never, in a class like this, ask you to memorize these formulas because we don't have the time to spend each day on the different ones. So I'm giving them to you, but we're going to do some problems together today. So the first formula we have is when we have a solid disk. So a solid disk is going to be the radius of that disk times its mass times a half, and that will be its moment of inertia. That's its resistance to change. So Vienna in Las Vegas is waiting for her number to be called on the roulette wheel, a large 3-kilogram disc with a radius of 6.6 meters. What's the moment of inertia of the wheel? So here's the formula, moment of inertia, that's capital I. So we have 0.5 times 3, so that's your 3 kilograms. Okay, and then we have the radius, do that right, 0.6, and then it has to be squared. So when I calculate that, I've got 0.54, and then the moment of inertia has to be whatever these are. So this would be kilograms, and these is the square of meters. So it's kilograms meters squared. Okay. Number 2. So this is a different configuration. This is a sphere, and the formula for a sphere turning around is going to be 2/5 meters, or 2/5 its mass times the square of its radius. So we'll do this, find what 2/5 is. So 2/5 is 0.4, and then I've got the mass. So the mass of the Earth is 5.98 times 10 to the 24 kilograms. That's a 4 kilograms. And then it says it has a radius of 6, and what's the moment of inertia? So how sluggy is the Earth to turn around on its axis? So it's 0.4 is 2/5 times its mass times its distance. Okay, and then we have to square the radius. Okay, so we've got 0.4, 5.98 times 10 to the 24 times 6.38 times 10 to the 6. When you calculate that, you get 9.74 times 10 to the 37, and then the first one is kilograms, that's mass, and then meters squared is going to be its radius. Okay. All right, you can see I messed up here. Whenever you have a straight pole, like a stick, okay, moving around its axis, so moving around one end, so like the minute hand of a clock or something like that, the formula for its moment of inertia is not radius, it's just the length of the stick, because you can almost consider that to be just one-dimensional. So it's still r if you think about it. It's a distance from the pivot point, but we call it length instead. So you've got a gymnast that's flipping around a bar, so that's the formula you would use, 1/2 m L squared. It's the same as r squared. Okay, so you've got 0.33, that's Olga, and she is, how big is she? 0.5, no, she's 50 kilograms. 50 kilograms. And then she has a length of 1.6 meters. Okay, so the first one is what's her moment of inertia. So this is easy, it's just what we've been doing before. Okay, times this, times 1.6, times 1.6. So her moment of inertia, or her I, equals 43 kilograms times meters squared. That's the first part. B says if Olga were to pull in her legs, therefore cutting her body length in half, how would this change her moment of inertia? Okay, well, if she's half as long, then this is half as long. Okay, so remember this is going to be squared, so it's not half. You'd actually have to take that half, square it, so it would have 1/4. You see, when you take a fraction by a square, you're actually making it smaller. So she would have 1/4 of the inertia. Okay, that's why just pulling in her legs straight like this to make herself makes her go 4 times faster. You can see that she can actually start accelerating fast when she brings herself in. And is that it? Just B? Okay. Back page. Okay. All right, what we got? Okay, we have a ring here. And a ring is going to have 1/2 mv squared. What was the disk? The disk was 1/2 mv squared. Okay. Okay, so it's the same, isn't it? So this is going to be 0.5, and her wedding band is 0.012 kilograms. That's okay, and then her ring is 0.6 centimeters. Now, you're going to have to say how many meters is that. So 60 centimeters diameter. They're tricking us. We need to find the R, right? So we want the R in. So first of all, we're going to have to say 0.3, because it's not 0.6. Its diameter is 0.6, so radius is half of the diameter, so it's 0.3. Then you're going to have to divide by 100 to get from centimeters to meters. So this is going to be 0.003 meters, and then you're going to have to square that. So what is that total? Total is going to be 5.4 times 10 to the minus 8 kilogram meters squared. Okay, so it doesn't take much for a wedding ring to spin on a table. That's very, very, very small. Okay, hickory dickory dock. The 20-gram mouse ran up the clock. Okay, first of all, I want to know how big he is, his mass. It's going to be, you're going to have to turn that into kilograms, so let's just go ahead and do that. It's going to be 0.02 kilograms, because you're going to have to move it 3 places to make it into kilograms. And then we need a couple different things. So first of all, you're going to have the L, remember here is angular momentum. If you remember when we did momentum, rho was equal to mass times velocity. When you're doing around in a circle, mr, m times radius, is essentially its mass times its velocity. So the capital letter L is essentially angular momentum. So it doesn't want to stop, or it's hard to get going. It's just momentum, but it's going around in a circle rather than a straight line. So I need to know some speeds. So I've got a second hand, a minute hand, and an hour hand, and they're all different lengths. So the distance around a circle, okay, is 2 pi r. All right, so remember velocity is distance divided by time. So 2 pi r is its distance, and then its time is how long does it take for it to go around. So we want all of this in seconds. So let's do the second hand first. The second hand goes all the way around it in 60 seconds. Okay, so we'll do second hand. So it goes around, and so when you do that in meters, okay, what is R in meters? Okay, it's 0.2 so it's 0.2. So it's going to be 2 times 0.2 times pi. Okay, I have a pi button on my calculator. Divided by 60. And we're going to get 0.021. And now we're in meters per second. So there's the velocity of the hand. I'm only going to do the second hand. The other is exactly the same. I'll just do the one here. Okay, so we're going to have, here's V. So I'm going to have L, which we're trying to find. Angular momentum is its mass. So we do that in 0.2 kilograms times its velocity. Its velocity we just found is 0.021 meters per second. And then times its radius. So how long is it? It's going to be 0.2 meters. Multiply all those together, and you have 8.4 times 10 to the minus 5 kilograms times meters squares per second. So we have a new unit. L, angular momentum, is going to be kilograms times meters squared over seconds. Doesn't all these units drive you crazy? Try to memorize them sometime. Please don't. Make you crazy. Okay, one more. In a physics experiment, Ingrid, the ice skater, spins around at the rink at 1.2 meters per second, with each of her arms outstretched at 0.7 meters from the center of her body. In each hand she holds a 1 kilogram mass. If angular momentum is conserved, how fast will Ingrid spin if she pulls her arms into a position of 0.15 meters from her center? Okay. This is a great question. I like this question. First of all, you know the angular momentum has to do with how much mass and where that mass is. So you've got 2 kilograms of mass, so you're not really interested in her body because her body is going to be the same in both times. The only thing that's different is where those kilograms are, where those kilogram weights are. So she's got 2 kilograms of weight, okay, and she's spinning them at 1.2, because if she's spinning, then the weights are spinning, meters per second. And then they are a distance from her body, so they are 0.7 meters away from her body, okay? So let's first of all find out what L is. L is going to be 1.68 times 10, no, just times 1, so 1.68 kilograms times meters squared over seconds, so that's L. And now she wants to know how fast she'll move. Okay, so we're going to do the same one where we're just going to solve for V. So we've got L, get V by itself, divided by MR. So we have 1.68 over her mass. Okay, her mass is, or the mass of the weights is 2 kilograms, times how far they are away from the body now, which is 0.15. So we've got 1.68 divided by 2 divided by 0.15. So we have 5.6 meters per second. Okay, now you're all smart.